Hello everyone, welcome back. This is 2-11 Methods of Compacting in the Compact Redstone series. I'm Immune222, and today I'm going to talk about the methods of compacting, of course, which includes some compacting concepts and principles, because these are going to be important for you when you're working on, for example, larger piston doors or more advanced redstone. And also, I'm going to talk about the other part of layout construction, which is powering layout construction, because I've only touched on piston layout construction in 1-12 configuration of piston layout. So I'm going to also touch on the powering layout construction part, because that is also essential in larger piston doors or when you're working on more advanced redstone. And finally, I'm going to cover a very specific topic on the top folded triple piston extender, the wiring techniques of it. So without further ado, let's get started. I'm going to touch on the compacting concepts and principles first. So there are four main ones that I want to discuss on. The first one would be called the grouping concepts. So the grouping concept refers to converting discretized piston layouts into easily executable groups. So essentially what this means is that we should group some pistons that have similar properties together such that we can wire it easier. And a simple example would be, say, a 2x2 piston door, although it's not really that complex in this case. So instead of having 4 sticky pistons like shown as this, you probably would see that this is a very absurd piston layout. You would probably want to group some pistons together if they have similar properties. So for example, we can have this bottom piston be replaced by moving this piston to here, because these two pistons have similar properties. They literally just push blocks into here. So similar for this top piston here. So we can also place it on the side. So because these two pistons have similar properties, so as these two, so we can basically just group them together, and we can also see that we can wire it easier actually, because we can just power the blocks here and we can just do our job. Although it's very simple for a 2x2 piston door, you can see in more advanced redstone that you sometimes have to group some pistons together for easier wiring. So this is also the reason why grouping concept is actually quite essential, although it might not be well shown in this case, because it reduces the complexity of circuits by simplifying piston layouts. So this often will reduce the volume needed for your circuits. And obviously we are talking about compacting our builds, so we would want our circuits to be simpler, let's just say. So that's why the grouping concept is essential. Now, another example, before I forget, is actually, well, essentially any piston layout involving large piston extenders. The grouping concept not only applies to when you build the piston layout, but also applies to when you actually wire the layout as well. Because here, you will definitely not want to wire this single quadruple extender by itself, and this quadruple piston extender by itself, and also this quadruple piston by itself. It is just not efficient, and you shouldn't do that in any case. And instead, what you should be doing is to wire all of these quadruple piston extenders as a whole. So the grouping concept also applies here. So you basically wire things that have similar properties together. So not only does the piston layout should be grouped when necessary, but also when you wire your redstone builds. So yeah, just keep that in mind. So that's all for the grouping concepts. Next, I will talk about another very simple concept. Is called the fold concept. So the fold concept refers to shrinking piston extenders using a folded setup. So it's very simple to illustrate. Here I have two triple piston extenders. So the left one would be a standard triple piston extender, just 3 pistons in a row, and the right one will be a folded triple piston extender. So you can see that we have a storage piston pulled aside. Now, the fundamental idea of fold concept is that it actually reduces the volume of piston doors, because normally piston doors the volume is determined by the length of the extender, in which case the standard triple piston extender would have at minimum 3 blocks tall in this case, but then for the folded triple piston extender will have at minimum 2 blocks in this case. So we can see the advantage of the folded triple piston extender over the standard triple piston extender, because the folded triple piston extender occupies a smaller volume, a smaller minimum volume at least. So that at least ensures us to have more compacting ability. So that is why the fold concept is important. Of course, one downside of the fold concept, or specifically fold extenders, is that it's obviously a bit harder to wire than standard extenders. So yeah, that's a major disadvantage. But then, hey, we are talking about compacting our builds. So obviously we might have to do some more complex layouts actually. So that's why we still have to use the fold extenders. So yeah, there you go. And that is the fold concept explained. I'll talk about another principle, there are no examples here, which is called the layout size principle. So the layout size principle refers to compacting a build until it has the same volume as the piston or powering layouts. Now, why does this principle make sense? Well, it basically arises from the fact that the theoretical smallest volume obtainable for any redstone build is the volume of the piston or powering layouts. So we should compact our build until we hit the layout size. It's that simple. Now, although the layout size principle exists, it tells you that you should compact your build until you hit the layout size. It doesn't mean that you can always do that. There are a few reasons, but mainly it's due to the powering layout. For example, the powering layouts may be larger than the piston layout. So another good example would be to show here is that, for example, we have this quadruple piston extender. Well, we cannot really wire within this 15 blocks, right? And we still need to have additional wirings. So for example, we might need these pistons with observers here. So we can see the powering layout actually may increase the volume up on the piston layout. So that's one reason. And another reason is also similar, which is that the powering methods would also require a larger volume to be achievable. So this is also a very good example, I guess, because you probably cannot really wire this in this volume here, I believe. So you basically need a larger volume, and you might also need some wires for it to wire the extender, of course. So yeah, that's when I say that the powering methods might need a larger volume to be achievable. So that is the case. And of course, later I'm going to be touching on the powering layouts, which will give you a more fundamental concepts or a fundamental baseline of that. So yeah. All right. So the next principle, it actually has a very similar name. I probably should have a better naming. But anyways, it's called the minimizing layout size principle. So literally just adding the word minimizing before. And this principle refers to compacting a layout until it's not possible or not feasible to be any smaller. So what is the difference between layout size principle and minimizing layout size principle? Well, layout size principle tells you to compact a redstone build until you hit the layout size. But then minimizing layout size principle tells you to compact the layouts until you cannot. So that's the fundamental difference. One is compacting a redstone build, and the other one is compacting a layout. So yeah, that's the fundamental difference. And you can hear when I say not feasible. So what do we mean by not feasible? It means that the layouts that are any smaller will have significant difficulty in wiring it. So of course this will require some professional judgment here. If I would, I might explain this in 3-4 redstone analysis. I'm not sure I'm going to explain it fully, but then yeah, it should be not that bad. It should be somewhat intuitive, that we should get some sense that if a layout has certain difficulty in wiring it, and that we should not compact it any further. So yeah, that's basically that. Now, if you have visited 1-12 configuration of piston layout, you might come across another principle, which is called the minimum piston extender length principle. Now, it's actually quite similar to the minimizing layout size principle, although they are not exactly equivalent. The reason is that the minimizing layout size principle might sometimes give you layouts that are not optimized in volume. So that's the fundamental difference. And as we are trying to compact our redstone builds to be as small as possible, let's just say, instead of focusing on minimizing the piston extender length, what we should be minimizing is the layout size volume. So that's the difference. And as a matter of fact, minimum piston extender length principle is just for introductory redstoning. And as we are heading on to the advanced levels of redstoning, we should really just abandon this principle, to be honest. So we should literally just follow the minimizing layout size principle more than to even consider the minimum piston extender length principle. So yeah, so let's just take a look at one of the examples. So let's just use the same example as in 1-12, which would be a 3x3 seamless cave door. Now, this would be what you would get if you're following the minimum piston extender length principle, which you would have 8 single extenders for these 8 blocks, and then 1 double piston extender for the middle block. Now you can see that these 2 pistons are sticking out, which is not nice because it actually adds to the volume, because we cannot wire it into a smaller volume otherwise. So how can we solve this problem? Well, the minimizing layout size principle will tell you, for example, this piston here, we can consider that instead of having this single piston extender here, what if we move it from other directions? For example, a double piston extender from the top. It works, although it's a bit more complicated, but then we actually shaved off a decent amount of volume. So same case with this here, we can just remove this and then just place it here. So you can see that by following the minimizing layout size principle, we actually shave 4 blocks in length just for this door, at least for the layout size. So yeah, you can see the fundamental difference between the minimizing layout size principle and the minimum piston extender length principle. So yeah, now it's also worth mentioning that from this example, although we have a free long volume for the layout size, it doesn't really mean that we can actually wire it within this volume, within the same volume as the layout size, to be precise. And this is also a very nice counterexample to the layout size principle, which is that, yeah, although the principle exists, it doesn't mean that it's always possible. So you can try to wire it, I bet you, it's probably not that possible, at least with the current technology, I guess. So yeah, there you go. So that is all of the concepts and principles that I have. So the next part would be the powering layout construction. So let's just recall the definition of powering layouts as mentioned in 1-12. So powering layouts refers to the additional wiring to the piston layout such that the combined layout can open or close the piston door by powering the layout in a specific order. So yeah, basically what's different between a piston layout and a powering layout is that powering layout, you have additional wires or additional redstone components to power the piston layout, where piston layout is only consists of pistons. So that's the fundamental difference, I guess. And of course, similar to piston layout, the most important thing of a powering layout is that it must be working or functional. Otherwise, what's the point of a powering layout? And we can check this similar to piston layout by powering, instead of the pistons, we power the inputs of the powering layout with, for example, different pulse lengths or constant signals, and see if the piston layout can do what we want it to do. So that's basically it. Now, that's all for the basic stuff of powering layouts, or the most important concepts. Let's head on with an example, shall we? So let's consider an expandable, downwards flush and seamless quadruple piston extender. Yeah, that's the full name for this extender. And let me just show you by building the site. Now, you can see that if we want to fully extend this quadruple piston extender, we have a problem. Is that if we power this dust line, which is the lowest that it can be, it actually cannot power this piston because it's too low, of course. So this means that we need to push in additional redstone components further down in order to power the piston at the lowest level. And a good solution would be to use observers. Because compared to redstone blocks, for example, observers, you can place it on the side of the piston stack without powering the piston stack. Whereas redstone blocks, you cannot do that, because if you have redstone blocks here, obviously it will power the piston right here. So you will need to retract it one block further. So yeah, that's not really that optimal. So we are going to use observers instead, because we can use observers, of course. And yeah, that will be the powering layouts before we place the input wires. Now head on to the input wires. So how do we decide on where we should place the input wires? The fundamental idea is that we should make sure that the piston layout is powered at all positions. Now, the lowest level has already been resolved by having this observer here, so we can remove this. And these two pistons, or these two levels, we can resolve this by placing dust line here. So this one powers, of course, and this one powers by quasi-connectivity. And a similar case would be placing dust wire on top of this dust wire as well. So similar logic, this powers directly, this powers by quasi-connectivity, and also we can just place another dust wire on top. So the same logic here. So you can see a trick here is that we can just place dust wires on top of each other, and by quasi-connectivity and direct powering, this actually powers the entire piston stack. So all we need to do is just to add an additional wire to this observer with pistons, and we get our powering layouts already. Now, in some situations or some powering methods, you might also need some updated pistons. So we can just add these into it if you need them. So that will be our full powering layouts, essentially. So shouldn't be that hard to understand, I guess. Now, as we are going to compact our redstone, we sometimes have to revise our powering layout. So if we consider this, this redstone wire here actually increases a layer on top. So we can basically improve our powering layout here. So of course, powering layout is not unique, and there are many other solutions. So if we want to reduce the volume induced by this redstone wire, we can simply just move this redstone wire to the side here as an example, and instead of having this configuration, we will slip in a wire here and then have some observers that will power these pistons. So this works. So yeah, this will be a 4-wire version and also compacted in the height of the extent. Now, although this exists, you can definitely wire it with this powering layout. I don't really recommend it because it's actually a bit more complicated due to some more complex sequencing reasons. And for me personally, I actually worked on this extender before, and this is actually the powering layout that I use. Although it is 5 long, which might seem not optimal, but then it's actually quite nice to wire it because I've wired before. So of course I know some business tricks for that. So yeah, you can try to see if you can replicate how to power this powering layouts. So yeah, have fun with that. Not going to go into full explanation, but then yeah, verifying if a powering layout works is also essential for you. So you should get the knowledge by trial and error by yourself. So yeah, that's going to be the section of powering layout construction. Now for the final very specific topic on the top folder triple piston extender techniques. Because why would I want to touch on this topic? Well, this extender is a fundamental extender commonly used in 5x5 patterned piston doors, and it also has some very specific techniques, and so I think it will be very suitable to include in this video, because you should start to know some techniques of wiring these triple piston extenders instead of using the standard triple piston extenders all along. So yeah, and wiring this triple piston extender actually requires knowledge of timings and sequencing. So timings, you already know this from 1-11 and 2-4, and sequencing, if you're watching in order, you haven't known any sequencing knowledge yet, so you can always refer to 2-12 Introduction to Planning and Sequencing for more sequencing knowledge. And of course, I'll also be further making a video specifically on sequencing, so that's 3-3 sequencing, and it will include some more advanced topics and techniques of sequencing, although I'll also include some of the techniques in here because I will illustrate them later on. It's necessary to do that. So out of all powering layouts, we'll just focus on this one because I think this is by far the best powering layout for the triple piston extender. Of course, there are also other ones, but then I would say they have major disadvantages in wiring it. So yeah, I'm not going to cover too much on that. So let's just focus on this one. So let me just build something here. Okay. So let's just see how we can power this extender. Well, powering C doesn't help. Powering B breaks things, so all we need to do is just to power A. That's the only move. And then now powering A doesn't help, it just reverts it. Powering C doesn't help, it just doesn't really do anything, but then we can power B. So yeah, we will start off by powering A and then we will power B. Okay, so now we get to some of the problems that we will first encounter. The first thing is that how can we get this bottom piston to spit out its block when it's extending, or retract its block when it's retracting? We have this redstone wire on a solid block, which will butt power this piston, but then to get it to spit, this is actually not that bad because we can simply just do a 1 tick or 2 game tick pulse, like so. And the middle piston updates the bottom piston such that the bottom piston will spit out its block. And of course it will retract it if it's in the retracting case. So yeah, also notice that when we power B earlier, the middle piston fires instead of the top piston, so this is actually very useful. And you can see why here. And yeah, if you're not sure why this powers the middle piston instead of top piston, it's simply due to racing condition. You should have learned this in 2-3, so I'm not going to go any more further into that. So yeah, so that's the first problem we can resolve, is that how to spit the block. The second problem is here, how do we get the middle piston to retract the bottom piston now? Because if we power A, we're going to power the top piston, If we power B, it does nothing. If we power C, no, that doesn't work. It will just revert again. Now, obviously, we can, not really that obvious, we can do some things like powering B twice, but then this is actually not a good solution, I would say. What we can do is that we can use timings. So, how should we time this then? Well, a nice solution would be to have, for example, a delay circuit like this. So let's just see how it works. So this will grab its block, and then A will power the middle piston actually, like so. And the reason, again, is due to racing condition. It's that simple. So yeah, just revise your piston powering properties and you will already know why. Now we come to this position and we have our final problem. How to retract this block. And the solution is actually exactly the same. Right? We just have a 2-tick delay. So let's suppose that this grabs the block and then it will power the middle piston. So by having another 2-tick delay to C from A, we can actually force this to power the bottom piston to power. Because if we power C at this location without any timings, then this will actually be locational, and we don't want that. So yeah, by using timings, we can actually force the bottom piston to power in any case. And the final thing would be to power B, of course. And a nice thing is that by using a double pulse, we can actually retract the entire extender, like so. So, very nice. Alright, so hence, we have the following sequence. So we have A, B, C, and then A with 2 ticks or 4 game ticks of delay. And then C again with 2 ticks or 4 game ticks of delay. And then finally we'll have B double pulse. So the 2 represents a double pulse. Alright, cool. So this sequence actually has a name. It's called the minimum move sequence because it's the minimum of moves that we at least need to power this extender. So hence minimum moves sequence. Now this sequence actually is not that bad, but then we can still improve it. And I'll tell you how now. And also before I move on to the improving of sequence, let me just mention this is that the technique of developing this minimum move sequence actually has a name. It's called assigning moves. And this will be introduced in 2-12 Introduction to Planning and Sequencing. Assigning moves is essentially just think of the moves that is needed to power your piston layout. And you should be able to do that because you are supposed to know how to verify if your piston or powering layout works. So by doing this step again, we can actually see if our sequence works. So yeah, it's literally the same technique, I would say, essentially. And yeah, now moving on to how we can improve the sequence. So there are 2 main things that we can notice. First is that B is powered with a single pulse first, but then with a double pulse later. And the second problem is that we later have CAC. And this is not repetitive. We cannot include the A before because the timings will mess up everything. So we cannot do that. Yeah. Right. So let's solve each problem one by one. So the first problem is the single double pulse issue, which we can resolve by either having a single double pulse toggle like so. This actually works quite well, although there are some disadvantages. First of all, I would say it's actually a bit larger than some other methods. And also you restrict yourself into powering this piston rather than having other places for inputs, because sometimes you might also have inputs here. So yeah, you restricted yourself into powering this single piston. So it might not be that nice. And second of all, it works well in this sequence, but then it might not in other situations. So for example, if you need to power B single poles, and then B double poles, and then B double poles, it's no longer a two-state sequence. It's a three-state sequence, and this can only cater for a two-state sequence. So yeah, sometimes this is not really that nice. Now, instead of using a toggle, we can actually think of another situation. What if we have this B single poles to be also powered by a double poles as well? Now, let's just see the consequences of powering this using a double poles. Okay? If I can. Alright, so we can repeat ourselves A, and then we can see if we power B with a double poles. We can see that this bottom piston actually gets retracted unintentionally by the middle piston. So that's not what we want. But then, how can we solve it? Well, consider this. At the first pulse, it will push this piston to here. At the second pulse, the middle piston will fire. But then we can also power C simultaneously, such that the bottom piston will get updated by the middle piston, and also split its block. So when this observer fires for the second time, this observer also fires. So that actually resolves our problem quite nicely. So all we need to do is just to induce some timings again. So that's that resolved. And the technique of removing this toggle actually also has a name, although it's not that necessary here. It's necessary in other sequences. It's called minimizing toggles. Yeah, and this technique will be introduced in 3-3 sequencing. So yeah, one of the more advanced techniques here, although not that necessary, I would say, in this situation. Now, let's solve the second problem, which is that CAC is not repetitive. Now, CAC is not repetitive because we cannot repeat things again and again, because reusing is actually quite important, I would say. So, what if we add another move to CAC? Well, what is missing? A. If we have ACAC as an example, or CACA as an example, then actually that's nice, because we can repeat ourselves by applying the same thing again. So in here, I would say it's preferred to have ACAC, mainly for these reasons. The first thing is that A is power first, so we can just have an input joint here, and we do not have to go from other places, and then we can just power this. Because if we have CA, we might block ourselves from powering A. And although you might have other ways to power A, sometimes it's not really that possible. So the input joints from A to C is slightly more preferred. The second reason is that, although it's not exactly specific to here, ACAC also provides us a very convenient way of powering this extender as well, if we have the correct input joints. like so. So having a 4-tick pulse here actually helps a lot with applying this. Of course, you will also need to time this along with B. So that's that. And hence, the revised sequence would be A, B, 2, and then we have A, 1 tick or 2 game ticks, then C, 2 tick or 4 game ticks, then A, 2 tick or 4 game ticks, C, 2 tick or 4 game ticks, and finally B2. And actually I also missed out C here, although it's not really that necessary. So A from A to B2. You can also insert a C here, which will be redundant, but yeah, it's also not that bad. Now, before you ask, why is A 1 tick or 2 game tick after B2? Well, because we are calculating from this observer here. So this induces a 1 tick delay or 2 game ticks delay. And hence, and since we need this observer to fire at the same time as this observer when this observer fires for the first time, so we would need A to be 1 tick or 2 game ticks after B is fired. And then for a second time, this observer will fire at the same time as this observer. So yeah, that's basically that. Now, before I miss out, and first off, this adding A to the sequence, it has a name. It's called adding redundant moves for reuse, and this will be introduced in 3-3 sequencing. And second, I guess it's also important for me to emphasize here is that we can see the essential concept of compacting from this as well, is that we should reuse as much as possible. So hence we have another concept that I haven't touched before. It's called the reuse concept. So yeah, the reuse concept is basically just telling you that you should reuse circuits, or yeah, you should reuse circuits if you can, and potentially develop sequences for reusing, because by reusing circuits you actually minimize a lot of need for specific circuits. So you might have a circuit that does a triple extension, and you might have a circuit that does quadruple extension, but then if you have a well-developed sequence, you might only need the quadruple extension circuits without needing the triple extension circuit. So essentially the reuse concept is important because you can compact your circuits, of course, because you only need one circuit to do all, instead of building multiple circuits that might do similar things or exactly the same things. So hence the reuse concept is important here as well. Okay, so that's all that I have for you. Now, before I head on to the exercises, I also would like to give you some resources. Now, I would say that the methods of compacting actually the most important thing that you should be doing is that you should learn by doing. You should practice more. You should do more redstoning by yourself. That's I think the most important thing of compacting any build. You should just do constant practice and you'll get better, essentially. And it's also preferred for you to look at some redstone builds built by some talented redstoners. So you can always learn from the circuits within their builds and try to see how they work. And you should also remember some specific circuits that might come across to be useful in some situations. So yeah. So by practice and memorizing useful circuits. Speaking of memorizing useful circuits, I've also done some videos on it, and specifically, one of them is 2-6, more on piston extender circuits. So you can check that video out. And also, as we are heading on to the sequencing and planning knowledge, I will also do videos on planning and sequencing. So they are respectively 2-12 Introduction to Planning and Sequencing, 3-2 Planning, and 3-3 Sequencing. So all of these you can just check out the playlist or in the documents if you want to. So yeah, I'll provide all the links for you. So let's head on to the exercises now. Alright, so the exercises I believe is quite simple. The first one is to ask you to compact this piston layout using the knowledge that you have learned from here. So shouldn't be that bad. The second one would be to compact, I should say, a powering layout, although it's more like a piston layout in this case. So yeah, apply some concepts here and try to compact it. The third one would be to construct a powering layout this time. So include updated pistons as well. And yeah, all of these have volume restrictions. You can just refer to it and yeah, just build it yourself. It shouldn't be that bad. And finally, of course, I will have an exercise on the folded triple piston extender. So this is a 5x5 seamless funnel door, and I want you to wire in 363 blocks with this given partial piston layout. And of course, it involves a folded triple piston extender. So you would need to use the wiring techniques, concepts, sequences, whatever taught previously, and apply it here. So yeah, it's better for you to learn by practicing, and so this exercise is specifically made here. And of course, the solutions will always be at the back, so you can remove this black wool wall or whatever, or just go to the back and take a look at the solutions. And yeah, and as always, the Word download and the documents will be available in the description below. And yeah, so thank you for watching. This video has been a while for me to upload, so thank you for your patience as well, and I'll see you in 2-2 Introduction to Planning and Sequencing, the final video for the intermediate topic series. So thank you all. I will see you in the next video.